الرنين آمن تمام ولا تخاف إيميليز انت بأمان.
Images were best in detecting infectious disease, tumor and swelling, aneurysm, strokes, sclerosis, hydrocephalus and spinal cord injuries. Oh, don't be afraid. MRI of the head is painless, so everything will be fine. Oh, don't be scared because MRI is safe and you will be alright. Ooh, ooh, ooh. Harmless, no radiation and no side effects on MRI. Ooh, ooh, ooh. One of the accurate scanning system in the world, MRI.
All right. See, MRI stimulates a lot of emotions in people. They create art, you know, and all sorts of stuff. And I think one of the reasons is probably that, can you hear me, by the way?
Yes.
Because you can see inside a person, and that is just, you know, it triggers a lot of thoughts, you know, a lot of emotions, and people would be able to actually look inside, which is pretty amazing, I think. All right, Anna, I think we're ready for the lecture. What do you think? I got all the equipment here.
I'm ready, but hold on. Oh, earphones. Watch out.
No, hold on.
Okay.
I got like my vacuum cleaner.
Uh-huh.
Yeah, I got all that stuff. So all ready for this lecture.
Very good. Let's clean up then.
To clean all the mess, you know, we're gonna create today. Oh yeah.
Welcome, EECS 16A. Woo!
Oh yes, participation.
That's right. Oh, all right. So today we're going to talk about, can you believe it's the 4th week?
Yeah.
You know what? So it's lecture 3A. This is because it's C type counting. You know, when you count an array in C programming language or in Python, it starts with a 0. So this is why it's lecture 3A, but we're actually at the 4th week. So pretty exciting. A few announcements. I'm super excited about today. Like my hands are kind of shaking. I don't know what's going on. It's like, oh, let me just relax. Maybe it's all the 10 cups of coffee I drank this morning. Yeah, I know. I shouldn't have, but I don't know. It just like happened. All right. So quest, folks. We have a quest today. Pretty exciting. Some of you is the first midterm you ever, or like the first exam you're gonna have at Berkeley. Congratulations.
No, they had 61A yesterday. That's what I was reading on the chat. We are not the first.
Oh man.
We tried.
Okay, all right. We are number 2. We're all right. No lecture on Thursday. Thursday, it is a holiday, at least for some, and so it's called Yom Kippur. No lecture on Thursday. I will pre-record a lecture for that. Just watch it at your own leisure. You know, get some snacks. You know, get some water, maybe coffee, or if you don't drink coffee, maybe tea, boba, and just like, you know, go like this, and you know, just look at all the definitions that we're going to cover in that lecture. So should be fun. All right, last time we talked about some proofs: linear independence and dependence, matrix transformation. and then proofs again, and then linear dependence and matrix transformation, because I just copy pasted it, and that's what happened. And today what we're going to do is we're going to continue with matrix transformation and talk about matrix inverses and vector spaces and all this good stuff. Good stuff. I don't know if we're going to get to vector spaces, but we'll see. If I keep on babbling, then probably we won't be. A few things about the quest today. I just want to remind you, okay, just for all of you that feel like, oh, stressed out. First of all, the quest is pretty easy. It is not meant to kill you. It meant to help you and really get you to the mood of being tested, which I think is a good thing, and show your knowledge. However, just remember, okay? So we give you the full trust. We want that trust back, okay? So not going to try any funny tricks today or anything like that. It's going to be just a solid exam, but we do expect you to obey by the rules of the exam. All right. Matrix transformations. That's pretty cool, right? Like, now this is funny. Ha, ha, ha. Oh, cosine sine minus sine. Oh, times alpha. Oh, it's on the side because it's a clockwise rotation matrix. It's pretty cool. But you know what? Matrix transformations are so embedded in what you do in everyday's life. I mean, have you ever thought about, here, let me just pull up something. That's my daughter, a few years ago. And, this operation that is being displayed here, you know what it's doing? What's the iPad is now doing on its probably GPU? It's just multiplying matrices, multiplying matrices, multiplying matrices, multiplying matrices, multiplying matrices in order to compute this transformations, either the zoom one or the rotation and shearing, all that stuff. This is just matrix multiplication applied on the GPU or CPU of that of the iPad. That is what it's doing. So it's really an essential operation. Everything that you do, like you go like zoom, like the pinch thing, and you zoom on your phone. That's matrix transformation. You scroll, that's basically you move stuff on a matrix, right? This is matrix transformation. Everything is just matrix transformation. Sometimes it is implemented by, by memory, shifts, but it's the same thing. It's all just calculated matrix transformation. So yeah, it's that's what it is. If you ever wondered, that's what it is. Let's see. Let's go back. All right. So when we talked about linear transformations before, is that what we talked about? Yeah, just a little bit of a wait. Yeah. We talked about matrix transformation before, and I feel like I covered this. Did I cover this? What do you think? You don't think so? Okay, well, that's great. Okay, so if we think about a transformation is considered linear if it satisfies pretty much homogeneity. Okay, so if I take a vector, so linear transformations on vectors, if I take a vector and I scale it by alpha, then it's the same as taking that vector, putting it through the transformation and then scaling by alpha. Okay, so whether you scale it before and whether you scale the result after, it should be the same. The other one is superposition. If I take two vectors and I add them together and then pass it through a transformation, that will be exactly the same as taking the vector and passing through the transformation, and then taking another vector, passing through the transformation, and then adding them together. Okay, these are the requirements for a linear transformation on a vector. Now, let me argue that a matrix multiplication is also a linear transformation. And pretty much the claim is that that it also satisfied a linear transformation. So how do I do that? Well, okay, I take X, I multiply by alpha, and then I pass it through a matrix multiplication. Well, that's pretty easy to show that alpha, this results in alpha times ax. So I can first compute a times x and then multiply by alpha. It will be the same as multiply a by x by alpha and then performing a transformation. In the same way, I can take two vectors, x and y, add them together, and then apply the matrix operation on them, matrix multiplication. Remember how you apply matrix multiplication? Like this and like that, right? That's right. And then you take x, you apply it, take y, you apply it, and then you add them together. That should be the same. And how do you show that? Well, you can show this proof just by explicitly writing the elements of each of the matrix and then just calculating and then showing that, just from a algebraic massaging point of view. And yes, alpha is a scalar. That is correct. Alpha is a scalar. That's a good point. Thank you for that. Okay. All right. So that's actually, I think I did cover this. It's kind of a background of what we did before, but what I wanted to talk about is in terms of matrix transformation, we looked at rotation matrices, we looked at reflection, but matrices can also represent, a system that operates on some state. Okay, so vectors can be representing a certain state. For example, if I wanted to represent a car at some time t, right? For example, my car just in my driveway, I want to be able to represent it in terms of, I guess, values. What would a car be represented by? Well, I can say its position, so where it is in a two-dimensional space, so x and y, that could be a position. I can also represent its velocity. Okay, for example, the velocity of my car right now is 0 because I'm not driving it. Nobody's actually driving. Okay. By the way, if I wanted to figure out where the car is going to be in an hour, or like actually in a second or so, is that all the information that's needed in order to be able to do that? Like if I wanted to see, from these values, can I determine where the car is going to be, in a second? Somebody says yes. Somebody say, I believe so. You need acceleration. You need a starting position. Well, I know where the starting position is. Let's say these are the position. This is the position. Is velocity enough to know where it's going? No, it isn't, right? Because I need to know velocity in what direction. So basically, I need to find what is the car orientation. If I don't know where the car orientation is, then I don't know where it's going to go, right? So it's not enough to know its velocity. I need to know its velocity in a certain direction. So that can either be described by Vx, Vy, two parameters, or I can just add one parameter, which is the angle that the car is right now oriented at. Okay, that's another way of doing things. So I do need either the orientation or Vx or Vy, and so I should probably add maybe a theta of t as part of that state in order to really represent it. Okay, and then when you describe a system, you have to think about that. I mean, is that descriptive enough in order to be able to estimate where the thing is going? Okay, velocity, if it's a vector, it defines direction. But if it's just a scalar velocity, you're going 90 miles an hour. Okay, well, am I going to the left? Am I going to the right? Am I going north, south? Like where? Right? In order to know where it's going. Okay. Now I want to describe a different, it's not a different, like a different situation. It's still a system. And that system is, we're going to see that across class many, many, many times. And it's the example of reservoirs and pumps. And you see that it's actually related to web traffic. It would be related to all sorts of things. But in this particular case, I'm talking about reservoirs and pumps. So I've got these three reservoirs, A, B, and C. We have a situation in California. We don't have a lot of water. And so we're going to store water in these reservoirs. Okay. And we want to know what's going to happen to those reservoirs. We're going to move water. We have these pumps that move water, all the time. So we can kind of figure out, okay, well, what is the dynamic of those reservoirs based on the amount of water that we move. And so the question is, what will be the state of the system? Anybody has an idea what will be the state? Like, what would be a good state in order to be able to track what's going on? How much water in each reservoir, right? We can represent how much water in each reservoir as the state of the system. So I can just write x of t, which be the state, as xa as a function of time, xb as a function of time, and xc as a function of time. Those would be the state describing how much water we have. Now I need to describe the dynamic, like what's happening to that system. Okay, like how things are moving. So I'm going to add pumps. They're going to pump the water and put it in different places. Okay. So this is, again, it's a column vector, right? Remember, vectors are always column vectors. All right. So, all right, well, I'm going to add pumps. And the pumps I'm adding through arrows in this particular graph. And I'm saying, you know what? And the pumps basically represent, for example, what would happen, how much water or, how much percentage of water are going to be, pulled out in a day. And then basically, it will give us the state for the second day. I mean, I can decide it's seconds, I could decide it's minutes, I can decide it's hours. Right now, let's think of it as a day. And again, it's a model. Somebody says Markov chains. Yes, you could also represent Markov chains in this particular way. Those they describe in this particular, in the context, this is just pumps and reservoirs. Okay, so what basically it says is that pumps will move water, and for example, they will move water from reservoir A, but then pretty much put it back, and then they'll move water from B into C, and they'll move water from C into B. And the question is, what will be then the state tomorrow? Okay, what will be the state tomorrow? Okay, so how do we go and figure out what will be the state tomorrow? So looking at those graphs, we would like to then populate what is really the system that describing this dynamic. Okay, again, I have a state vector representing the amount of water. And then, the flow rate with each pump is like one, like it's written on these edges here. It's 1, right? So a fraction of 1, the entire water from A will be pumped back to A. The entire water in B will be pumped to C, and the entire water from C will be pumped to B. Everybody's okay on the setup? Did I say that I have a vacuum cleaner next to me? Did I say that? Okay. All right. So what will be the tomorrow? So we need to kind of maybe derive what's going on. Okay. So let's try to see if we can represent it as linear set of equations, right? So what does it mean to have this arrow over here? Well, pretty much what it means is that x of A, x sub A, so the water in reservoir A at t plus 1 equals to what? Let me argue x of t, because we have this arrow pointing out here. So all the water are going to stay. So the next day, all the water, oh yeah. Thanks for correcting me. X sub A of t. And what about the water in B? Well, x sub B of t plus 1 will be equal to, well, all the water from B tomorrow are going to be the water that were in C the previous day. So it's x sub C of t. And then x sub C of t plus 1 will be equal to x of B of t. Okay, so this is the dynamic described by linear set of equations. Well, if I have linear set of equations, I know I can represent it by a matrix times a vector. Isn't that amazing? Right? So I can represent these transitions as a matrix multiplication, like this and like that. Yeah? All right. So I can basically write in a nicer way. These are the set of equations, but then I can also write it as a matrix multiplication. Now I need to populate it. So what will be the population? Well, xa t plus 1 will be 1, 0, 0. Okay, that represents this particular equation. And then I will then say, well, xb t plus 1 equals x of c. So that will be 0, 0, 1. And that will represent this equation. Remember, like this and like that, right? So the little finger is multiplying x of c. And then the last one, let's pick this color, would be 0, 1, 0. Okay. Are we good? Yes, this is a finite state machine. What's the number of states? 3. All right. Well, that's great. Oh, nice handwriting I got here. All right. Or we can write it as xt plus 1 equals some q, which is the transition matrix, times x of t. Okay. Now, is the water being preserved? The total amount of water being preserved in the entire system? Yes, it would be. And you would be able to, we'll show at some point that is actually the sum along the columns. If that sums to 1, then that will be conservative type of system. But I'm just going to throw it out there just for the sake of it. And the question is like, what will be the state after 2 times now? Well, let's, 1 day passed. What happens after 2 days? What happens after 2 days? Well, okay, well, let's see what happens after, from day 0 to day 1, we know what happened. Well, it's just this multiplied by q times x. And what about day 2? Well, day 2, x of t plus 2 would be equals to q times x of t plus 1, right? That represents the dynamic. But I know what x of t plus 1 is. It's really much q times x of t. So now I've got q squared, or q times q. Okay, so effectively, I can write it in this particular way, and q square is actually a matrix. Okay? So a matrix can represent, a lot of things. Here it represents the dynamics of 2 days. Okay. Okay, q again is this transition matrix. This is q.
Mickey, before you continue,
yep.
Can you explain where Q represents again and how you found these values for the matrix? There are quite a few comments in the chat.
Oh, how do I find? Well, okay.
Yeah, just go back a little bit.
From this graph, right, I wanted to see what is the dynamics. Well, water is being pumped from A, and they're all going back to A. So the state x of A, the amount of water at the next day is the same as the amount of water in the previous day. Okay, it has not changed. That arrow says that it's not going to change. All the water are going to pretty much stay. What happens to B? Well, all the water from C are being pumped into B. So the next day, all the water in B are going to come from C. So x of B at t plus 1 the next day is going to be x of C of t. Okay, that's a linear set of equation. It's just an equation describing what will be B in the next day. And then what about C? What would happen to C? Well, all the water the next day are going to be pumped from B into C. So x of C of t plus 1 will be equal to x of B. This is a linear set of equations. Linear set of equation can be represented by a matrix multiplication. And I'm going to write that as a matrix times a vector. Let's see what this matrix actually says here. 1 like this and like that, right? 1 will multiply XA and the rest are 0. So the result of XA t plus 1 will be XA. That's the same as this. X of B equals X of C, right? So let's see for the second row. Well, it's 0, 0, 1, like this, like that. The pinky finger is going to multiply XC. And so X of B, T plus 1, will be equal X of C. Okay, that's what this matrix multiplication is representing. And now I'm going to call this matrix Q, and I would say X of T plus 1 equals Q times X. That's the state. And then this is what's going to happen to that state after 1 day. All right. Okay. And then the question is, what would happen after 2 days? Well, at day 2, it will be the same as Q times the state at day 1. But then I can go, well, what is the state at day 1? Well, the state at day 1 is Q times the state at day 0. So effectively at day 2, it's Q times X of T, which is also can be written as Q squared times X of T. So I can propagate the state and know what is going to happen, let's say in the nth day, by taking Q to the power of n multiplied by my state now, and I know what's going to happen in a week, if n is a week, if n is 7. Does that make sense? It just looks at the state, like how the state is changing. Okay, so let's say the state at today is 101. What does it mean 101? Well, there's water here, there's no water here, and there's water here. Okay, this is full with some value, I don't know, 1 million cubic meters, I don't know, some number. This is 0, and this is 1, 2. And the question is, what is the state at t equals 1 or t equals 2? So at tomorrow or the day after tomorrow. Okay, so how do we go and find that? Well, what we're going to do is just go and multiply this. So, okay, so I can just take X of 1 would be equal to 1, 0, 0, 0, 0, 1, 0, 1, 0 multiplied by 1, 0, 1. And that would be equal to, well, like this and like that. And I would get a 1. And then like this and like that. And I would get a 1. And then the last one is like this and like that. And 0 multiplies by 1, 1 multiplies by 0, 0 multiplies by 1, so I get 0. So that will be the state tomorrow. Does it make sense? Well, it kind of makes sense. If there was water here, they flew into B. So now there's water into B. Water in A stayed, so there's water in A. What about C? Well, all the water from C were pumped, but B didn't have any water, so no water's in B. So yeah, that makes sense, right? All right. So then this is effectively what happens in day 1. And then if I want to calculate what happens in day 2, I would take this state and multiply it by the same matrix. And you see that now I'm going to get 1, 0, 1. So if I have water in B and A, the next day I will have water in A and C. And that's basically what it says. This is the water in A, this is the water in C, and this is the water in B. So if I had water in A and B, the next day I will have only water in A and C, just based on this graph. And so this matrix multiplication actually represents that. I could have also calculated Q times Q times the first vector. Well, if you actually calculate what is Q times Q, if you do that, it turns out to be an identity. Now, why is this an identity? Well, think about that. What happens at time 0? We had a state 101. After 2 days, what am I getting? 101. It's the same thing. So Q times Q must be an identity because it didn't change the original state. Now, does it mean that Q times Q is always identity? No, it doesn't mean. In this particular case, it is. Okay, but it's not a general thing. Can you converge in this particular case? I would argue no. It doesn't converge. It always oscillates. Either water are at C or at B, moving back and forth, moving back and forth. So it's always oscillates between these two states, right? So there's really no convergence into a state that is a steady state in this particular case. I just decided that, so somebody asked like, where did I plug this vector? Well, I just decided that this was the state. But that's what happens today. This is Lake Shasta. This is, I don't know, San Pablo, and this is some other lake. I don't know. And then I just pump water. I just told you what the values are. And then we just wanted to see, based on this dynamic, what's going to happen tomorrow. All right. Okay. So what if I have this state transition matrices? So can that actually happen? Is that realizable? Is it real? Is it for real? Like I have, reservoir A, reservoir B, reservoir C, and then the next day I'm going to get half of reservoir A into A, and then half of reservoir B into C, and half of reservoir C into B. Is that realizable? Like, is that real? Yeah, why not? I mean, like, pretty much, we pump half of the water, but half of the water evaporates. This is what happens, But that can be a situation. All right. So I want to write that as a system, as a matrix of equations. So what I can do is I'm going to say, x of A at t plus 1 equals half of x of A at times t. And then x of B at t plus 1 equals half of x sub c of t. And then x of c at t plus 1. Look how horrible my handwriting is, right? Half of x b of t. Okay, these are the linear equations. I can put that again in the matrix form. Oh, my God. I can put that in the matrix form, and magically it is the same. Okay. Half of the water from state A will stay the next day. Half of the water from state C will go into B, and half of the water from state B will go into C. Okay, you have to do this, like that, and figure out which part is getting the water. And now I can ask all these questions. For example, what would happen after 2 days? Well, I'm going to take this matrix Q, which is a transition matrix. I can take this matrix Q, which is the transition matrix, this is the Q, and then just square it, and that would be, representing what would happen after 2 days. And if I do that, then it's pretty much taking Q times Q. I can do this calculation, like this and like that. What do it give us? It will give us a matrix, which will be 1/4 in this position. And then like this and like that. What is that? Like this times like that. That would be 0. And then like this, then like that. Nothing overlaps. All the zeros are multiplying, and I get 0, and so on and so forth. And that ends up being a diagonal matrix that has fourth on the diagonal. Okay, if you just do this matrix multiplication, that's what we get. So after 2 days, basically all the reservoirs will have fourth of their values. Okay. That is what the system represents. Okay, it's a leaky system. And so the question, what would happen after the 3rd day, 4th day, 5th day, and day infinity? What would happen there? Well, per zero, yeah, we're just losing fourth of the water every 2 days. Every 2 days, we're losing fourth of the water, right? So the numbers will diminish to zero. And so this is non-conservative system, and you can actually see that the columns don't add to 1. Okay, so is that a real system, non-conservative? Well, let me show you a system like this. This is the Dead Sea in Israel, the lowest place on Earth. In 1984, it was minus 397 meters below sea level. Okay, so it's pretty deep. It's like 1,200 feet or so, just a little bit less than that. And then this is Google Earth, and just take a look at this and see what happens till 2010 or so. So pretty much disappearing. Okay, so that I can represent by pretty much a system where I have A and then I put an arrow into it, and that arrow is less than 1. Okay, that can be represented. If the state of the water, I can actually say, you know, this is A, and then maybe 0.9 or something like that. That may be representing, or that would be really horrible if it was 0.9, because we would lose it very quickly. How about 0.99? So every day, every year, it just decreases by 1%. Okay, and keep on going and going and going. Does that make sense? Now, still a wonderful place to be. If you now do a matrix operation and zoom in, you would recognize one of my colleagues, which turns out to be, yeah, that's right. You know, it's very, the salinity is super high in the Dead Sea. So you just basically float. It's very hard to actually sink in those waters. And it's the weirdest thing possible, you know, so I highly recommend that. All right.
It was wonderful.
That's right.
Quite cold, quite cold.
Well, it was winter, it was January.
Yeah.
So it's, you know, it was 75 degrees water in January, all right? So cold. Right. All right. What if we had a 2 instead of the half? What would that mean? I can go and write those equations again. And I will end up with a matrix that looks like this, with 2's at the place where we had half before, right? This, you know, this didn't change. And then the question is, what would happen the next day? And so, and maybe after 2 days. After 2 days, the amount of water would be quadrupled in every reservoir. Is that possible? Well, maybe. But here's an example of such situation that you can represent that. And what happened if we keep going? You know, it's going to explode. Yeah, maybe raining. And so numbers will explode to infinity. So here's an example. Can you see it? Whoa. Did you hear the sound?
No.
I don't hear sound either. I don't know. Yeah, I don't know what happened. Anyway, so this is a big elephant toothpaste. It's called. It's basically you take what's the name of this water? H2O2. Do you remember what the name of this? I forget. You're muted. Do you remember what H2O2 is? Yeah,
Hydrogen peroxide.
hydrogen
Yeah.
peroxide, yeah. And then you add some catalyst and basically all the oxygen comes out and you put soap and that's what happened. So yeah, so if I wanted to represent this dynamic, maybe I can represent it using something like that, maybe. Okay. All right. So here's a system, and it's basically a graph representation representing those pumps, right? So I have 3 reservoirs, A, B, and C, and I want to keep track of how much water in each one. And then when I turn on some pumps, water moves between those reservoirs, and where the water moves, that the fraction is represented by the arrows. Okay, so in this particular case, half of the water went from A to B, right? And then half of the water will go from B to C. And then third, let's say, of the water will go from C to B. Now, why is that? Well, it's just like, this is the system. I don't know. I mean, like that's given to you, and that's the system. Okay. And now the thing is, you can ask, okay, what does the rest of the water go if it's a conservative system? Well, you have to actually make sure that all the water are accounted for. In that particular case, half of the water, let's say, would stay in A. So we need to label that. So half of the water, let's say, stay in A. And then third, let's say, stay in B. And then, maybe 6 goes over here, and then, 2/3 over here. So now you can kind of see that everything is accounted for. A moves half of it to B, and half of it stays. B moves half of it to C, 6 of it to A, and then third stay. And that pretty much all sum to 1. And then for C, third of it will go to A, 2/3 stay. Again, that sums to 1, and that's basically summing the columns of that matrix that we're going to be representing. A, B, and C in just the graph representations are called nodes. The arrows are called edges, just from a notation point of view. Yeah, it could be probability functions, by the way. It could be, it could be many things, but in this particular case, we're talking about pumps. And then the edge weights, the fraction represent edge weights, okay, these fractions. And that is the terminology in graph representation. And this is a directed graph because the arrows actually have a direction as opposed to not having a direction, okay? So that is just some definitions. Now, the question is, can you tell how much water in each of these reservoirs after the pump starts? Can you? No. You need to have some initial, like you need to know what the state today to know what happens. If you don't know what the state today, it doesn't mean anything. Okay? So you need to know the initial amounts, and then you will be able to see what happens. Okay, so you have to know some initial condition in order to be able to do that. Okay, so let's try to fill this particular one. Let's fill this in the matrix. And how do you do it? Well, the safest way of writing things is writing first equations. Okay, so what is A in the next A? So I would say x of A at t plus 1 equals to, well, half of A, half of xa at t, plus, what else it's getting? Well, it's getting from B 1/6. So 1/6 of xb of t. And then it's getting how much from C? It's getting 1/3. Okay. It's getting 1/3 of x of C of t. And so I now I can fill the first equation, and pretty much is A to A will be half. And then B to A, which is this is B to A, will be 6. And then C to A would be 1/3. Okay. Now I can write the second equation, and I'm going to do the non-safe way, which let's think of what happens, how they move from, the second row pretty represents how things move into B. So the first column represent A to B. The second one is B to B. And then the third one is C to B. And those, if I look at the graph, A to B, A to B would be half. So I'm going to put half. B to B is going to be third. And then C to B is going to be C to B, 0. That's right, nothing moves. And then I can go and write the last set of equations that are representing A to C, B to C, and C to C. Okay, so this is the structure. But again, the safest way for you to do it is write the equation and then put it into the matrices. If you got it, then you can be quicker by looking at the graph and putting this, but don't do that on an exam. Okay. All right. So this is effectively the matrix, the transition matrix representing this particular graph. Okay. Let's do it again. Do it again. I'm going to go from, again, this is a different graph. This is a different graph. And I have A. A is now getting how much from A? A to A? 0. Okay. B to A? 1. C to A?
0.
0. That's right. It's a directed graph. What about second column representing, like this and like that? So basically A to B, right? From A to B. This is this value. A to B would be half. And then B to B, 0. And
0.
C to B would be a 1. And then the last one would be A to C, which is a half. B to C would be a 0. And then C to C would be a 0. And this is the matrix that I have.
B to C is 1, I think. It's a double arrow.
Oh, that's a mistake. I'm sorry. That's left from, there you go. Sorry about that. We would never write that in a directed graph. We'd only have then 2 arrows, okay? There's just a small typo. I apologize for that. Okay. So we have this state, and let's say we know x of, we know x of t plus 1. Can we go back and from x of t plus 1 calculate back x of t? Can we calculate the reverse? I know what is, somebody tells you, oh, I know what is the state tomorrow. Can you tell me, and I know the transition matrix, can you tell me what's the state today? Can I do that? And the first question I'm going to ask you is like, will flipping the arrows make us go back in time? Like if I just flip the arrows, can that safely bring us back in time? I'm just going to flip the arrows in this graph. Does that represent the reverse?
Wouldn't be the same.
Well, let's see. Okay, this is the arrows flipped. Okay, typo corrected. This is in the reverse. And what will be then the matrix? Well, the matrix in reverse, A to A is 0.
0.
B to A, half. C to A, half.
Half.
A to B,
1.
1. B to B, 0.
0.
C to B, 0. And then A to C, 0.
0.
B to C is a 1. C to C is 0. Okay, well, that is the matrix. And so this is what it is. And now let's see what happens. If I take 4, 6, and 8, and I multiply, this is just an example. I just pick those numbers and I want to see what happens. 4, 6, and 8. So if that was at t equals 0, then at t equal 1, like the next day, I would get 6, 10, and 2. How do I calculate this? Like this and like that, like this and like that, like this and like that. All right. So this would give me these numbers. And now I'm asking if I put here 6, 10, and 8, sorry, 6, 10, and 2, would I get back 4, 6, and 8? Well, let's see. 0, half, half times that. Well, it's 5 plus 1. 5 plus 1 is 6. Yeah, 6 doesn't equal 4. So I'm not going back in time. So effect actually 7. 5 plus. Oh, I guess a mistake, huh? Anyway, 6 does not equal a 4, and then and so on and so forth. Basically, this vector is not equal to this vector, so it's not the inverse. Reversing the arrow is not the inverse, but it is an operation, and that operation is actually called transpose. So in general, doing this transformation doesn't. By the way, in some cases it would do. Flipping the arrows in some cases would actually work, but we'll talk about that later. That operation that we talked about is the matrix transpose. Okay, remember that we had a vector transpose, right? A vector transpose took a vector like this and made it into like that. Okay, that's what it made from a, and so the matrix transpose basically does the same, but for matrices. And so if you have an n by n matrix that its elements are I, j, a transpose of the matrix will make you an m by n matrix with the elements being ji. Okay, it flips those elements. It is not in general an inverse. Sometimes it is for very particular matrices, but it's not in general an inverse. How do I calculate this? Well, if I look at the columns of the matrix A and I think of them as vectors, then effectively I will take A1 and I will transpose and put it here. And I will take A2 and I will transpose and put it below. And I will take A3, transpose and put it below. And I'll take AM and transpose and put it below. That's a matrix transpose. For our particular case, so this is M by, if this is N by M, because the size of the vector A is N in length and there's M of them, then this one would be an M by N matrix. Okay, so if I have this case, 0, half, half, 1, 0, 0, 0, 1, 0, and I want to compute a transpose, well, the transpose, I will take this one and transpose it. I will get 0, half, half. And then I will take this one and transpose it 1, 0, 0. And I will take this one and transpose it 0, 1, 0. And that's kind of what we got when we reverse the arrows. Okay, that's exactly the matrix. So it was a transpose. And so this is the result. Okay, this is transpose. Now I want to talk about matrix inversions. We want to invert a matrix. Well, this is a really example of a inversion of an operator. If you have X and you staple it, then unstapling it will give you back X. Okay, I love this example. It's from Laura Waller. So basically you're reversing that operation. Here's a page. This is a manual for the desk that I just have. Is that a reversible operation?
Just print another one.
Oh, that's not reversible. That's just duplication. Oh, yeah, kind of. I can reverse this folding. It's wrinkled, but I can iron it. Okay, so it is reversible. Okay. What about this one? Is that reversible? Well, if you ask my daughters, take a tape. Put it back together. Kind of reversible, right? Now, what about this? Is that reversible? Is that
You need
reversible?
more daughters.
Not reversible. But remember, we still need to clean it. All right.
Ears.
All right. Makes sense, right? Okay. So let's think about the case, back to our case, right? Of matrices. We have x of t plus 1 equals q times x. Okay? And the question is really, is there a square matrix P? If I want to go back in time, right? Is there a square matrix P? And I'm actually emphasizing square because these are, again, square systems that we're going to transition matrices are square. Then is there a matrix P such that we can go back in time? So P times x of t plus 1 will be equals of t, x of t. Is there such a thing? And somebody says, oh, yeah, if the matrix, like if I look at the chat, if the matrix is invertible and kind of stuff like this, yeah, but what does it mean? Okay, then we're talking about now the meaning of this invertibility. Okay, so is there, for example, a tape matrix that would then go and stitch back my page that I just cut with scissors? Okay, and the answer is yes, but under a condition that P times Q will be equal to the identity matrix. Basically, if P times Q will be equal to the identity, then I can just go back in time. Now, how is that going to work? Well, the way it's going to work is, well, x of t plus 1 equals q times x of t, right? That's from this equation. If I multiply by p, so I'm going to take this, what's tomorrow, multiply by p, and I'm going to take this is also what's tomorrow, multiply by p. If I want to go back in time, right? If this is identity, if p times q is identity, so identity times x of t will be equal to p times x of t plus 1. So this is basically the reverse. If that is true, if p times q equals the identity, then x of t equals to p would, basically would be go back in time. Does that make sense? So I can then claim that if I multiply, if p satisfies that, then I will get I times x, which is pretty much saying I can now calculate back x of t from x of t plus 1. How? Multiply by p. But what I used here, I used the fact that pq equals I. Okay. As a consequence, by the way, it turns out that q times p, remember, matrices don't commute necessarily, but in this particular case, q times p is also an identity. And I can show that pretty easily. I'm going to take this equation again and saying, x of t plus 1 equals q times x of t. Well, what I can do now is says, you know what? Hold on. What is x of t? What is x of t? Well, x of t equals p times x of t plus 1. I can substitute P times x of t plus 1 instead of x of t. And when I substitute it, this is what I get. It says that x of t plus 1 equals something times x of t plus 1. If that is true, what does q of times p have to be? An identity. Okay, so if this is true, then the converse is also true as a consequence. All right. So here's a definition, a formal definition for a matrix inverse. Still have paper in my foot. It's kind of nice walking around it, on it. It's kind of like smooth and stuff. It's pretty cool. All right, so here's the definition. Let P and Q be square matrices. This is how I write square matrices, okay, in math language. Okay. P and Q are in R and n by n. That's basically what it means, square real matrices. Okay. P is said to be the inverse of Q if P times Q equals Q times P equals I. Okay, that's the definition. And then if that is true, we can say that P equals Q to the power of -1. But this, what does it mean to the power of -1? It's just basically, that is the definition of Q inverse. It's just a notation. Like, you know, for scalars, you can take A and then compute 1 over A if A is not equal 0. But you can't do that with matrices. Okay, matrices doesn't work. But we use the same notation. So A to the -1 equals 1 over A, because and then if I take 1 over A times A, it will be 1. So that's in the scalar lingo, is in, you know, identity matrix. You know, you take the inverse, multiply, and that works. Doesn't work for matrices. Like, you can't just take 1 over, like, it doesn't work. But we use the same notation. We're overloading this notation. This is really what it means. P times Q, Q times P equals I, the identity matrix. What about non-square matrices? Okay, let's see who's listening to this lecture. Lower your volume, move your, move your headphones a little bit. Okay, let's see if you're listening. You didn't listen, Yakir. You didn't listen. You need to pay attention for this lecture. You need to pay attention. That's my point. Okay, anybody that hurt, that's because you're not paying attention. All right, square matrices, 16b, not in this class. We can do stuff about square matrices. It's called pseudo inverses, because they're not really inverses, but we're talking about 16b. All right. Okay, well, in our particular case, remember, we had this, right? And we had this system. Now we want to compute a P, which is Q to the -1, the inverse, right? We still want to go back in time. Flipping the arrows did not work, right? Flipping the arrows did not work. So we need to find a P, which is the inverse of Q, such that x of t equals P times x of t plus 1. We need Q times P equals identity, or P times Q, the same thing. How do we find it? All right, thank you. That was a nice, this is like it's a moment, right? It's a moment. It's a moment. Let's do this moment. We need Q times P equals I. What we're gonna do is pose this as a set of linear equations, which we can then solve via Gauss elimination. Yeah. Sweet, huh? I know, it's amazing. So what we want? We want Q times P to be equal I. Q is the matrix. P unknown. We don't know what P's are. P could be PP. We don't know. P. Who knows? Well, we know what P is, but it's not the P. We need the letter P. And I is the identity. Okay, is that a linear set of equations? Yes, but it's not what you're used to seeing. You're used to seeing something else. So I'll just disguise it into what you're used to seeing. How about that? Is this a linear set of equations? Well, that's a Q. That is unknown vector. That should be equal to B. Can you solve that? Yeah, you can solve this. What about then the second row? Well, second row, pretty much I can call this P2. And so Q times P2 should equal to B2. That's another solution. And then of course, the last one is Q times P3 should be equals to B3. So effectively, I need to solve 3 sets of different linear equations. Okay? That's what I need to solve. Can we do that? Yeah, we need to do 3 times Gaussian elimination. But you know what? If you remember, Gaussian elimination really operates on the left side, and the other numbers just show up. You know, these numbers just are manipulated by the left side. So can we effectively solve all of them at the same time? Because if remember, it was just making this effectively a upper triangular matrix and then convert it into a diagonal matrix. But these numbers were just moving along, you know? So we could just move them along at the same time. So here's how it's done, okay, in an efficient way. We're gonna create an augmented matrix, but instead of having a line and one vector after that, we'll just have the rest of them. And manipulate this to be upper triangular. And then these would be manipulated by the same operation. And then after that, we're gonna do, make it into a triangular one, to a diagonal one. And then again, these will be manipulated. So we are solving it at the same time, just saving time. We could do it one at a time, but like, why? This is much easier. Okay, so let's think of it. What will be the steps? Well, I have 0, 1, 0. I don't like it. What do I need to do? I need to flip those 2 rows, right? Well, I'm going to flip all of these together. That's what it means solving them together. Okay, so effectively, I flipped these 2, and I got this. Okay, what's next? This is half. Right? I don't like it being half. I'm going to multiply by 2. This one, multiply by 2. If I multiply by 2, I will get 1. Half times 2 is 1. 0 times 2 is 0. 1 times 2 is equal to 2. And then the entire thing, so 0, 2, 0. The rest is being copied. Okay, what about now? I need to then, okay, this is already eliminated. Now I need to eliminate this one. Okay, so 2 times that minus this. 2 times this minus that. And you know how to do it, so I'm not going to repeat Gaussian elimination. You should know it by that. So when I do this, I get minus 2, 2 here. Okay, just multiply that and then subtracted this. Okay, so this is what I get. Well, that's pretty close. Now all I need to do is eliminate this 2. And then because already right now it's an upper triangular. Well, I have a 2 here I don't like. I need to divide by 2. Right, and then I need to eliminate this one. So you can do that in 2 steps. And that's what it ends up being. Okay, again, Gaussian elimination, nothing new. I just did those 2 steps. You should be knowing that really well by now for tonight. All right. Well, folks, now I have a result. This is pretty much the matrix. This is I, and this is P. So we started with Q and I, and then we ended up with I and P. So by starting with diagonal here and then Q, we made, the first one I, and then the other one, ended up being P. Okay, this is how we find basically P, the inverse of Q. Let's see if it works. Okay, well, we had this situation, right? 4, 6, 8, result in 6, 10, 2. Let's see if it goes back. 6, 10, 2. Multiply this, 0, like this, like that. I get a
4.
4. Like this, and like that. I get a 6. And like this. Oh, like this, like that. Okay, you can see that is an 8. All right, so yes. And if I actually compute this times that, you'll see it's an identity. This times that will also be an identity. So I found a way to calculate now the matrix inverse. Now, the cool thing about it is, if we wanted to solve a linear set of equations once, we can do Gaussian elimination on that once. But let's say we have the same operation that we need to do all the time. If we calculate now the matrix inverse, well, then we don't need to do Gaussian elimination to solve the next problem. We can just use that inverse matrix to solve immediately the next problem and the next problem and the next problem. So sometimes it's worth actually computing the matrix inverse, even though there's a little more calculations, because it saves us time. And we went back in time. That is correct. Beautiful. And now we can actually take a number of steps. We can go a week. We can go a week. Anybody wants to go to 1984? When they introduced the Mac? Yeah. Okay, so the question is, can we always invert a function? Right, this is the this was the staple, and this was the unstable. Can it always be true? What about this function? Not linear, but can we invert it? Why not? Let's say x equal 2. So f of x equals f of 2 equals 4. How do I go back? I take the square root. Right? So it's 2. Yeah, it's invertible, right? How do I go back? Well, it's a square root operation. Square root of 4 equals 2. Okay, take your ears and stuff. Prepare. No, because f of -2 is also equal to 4. And I have now uncertainty. I don't know, actually. Is it 2? Is it -2? I don't know. So I cannot really invert. There's a mapping of 2 values into 1. Okay, that could be a problem. Okay, so not inverted. What about this one? Can it be inverted? Everybody's saying yes. Okay. Let's see. Let's say a equal 0. Okay. A equals 0 and x equals 2. Okay. So f of 2 equals 0 times 2 equals 0. Can we invert it? No. What about if a equal 1? Well, let's see. F of 2. Well, 2. Let's say a equal 2 equals 2 times 2 equals 4. And I can go back by dividing by 2, by dividing by a, right? So I can only do that if a is not equal 0. So yes, This is invertible if A is not equal 0. So if A is not equal 0. And now we have A times X, where A is a matrix. And I forgot actually to do that. And the question is, can that be inverted? And somebody might say, yes, maybe, as long as 1 minus A is not equal 0. Ugh, hurts, right? Like there's no such thing. Okay, there's no such thing. Well, basically, the answer would be yes, as long as A to the minus 1 exists. If A to the minus 1 exists, then I can invert it. And the question is like, when does it exist? I'm going to give you a theorem. You know what's beautiful about a theorem is that basically you have a test to check. Ready? Theorem. Invertibility of linear transformations. A is invertible. That means that it has A minus 1. If and only if the columns of A are linearly independent. We learned what linear independence is, right? Like we know what it is. And we know what linear dependence. Pretty much the consequences of this sentence says the following. If the columns of A are linearly dependent, then the inverse of A does not exist. It also says if A to the minus 1, like if the inverse exists, then the columns are linearly independent. So it basically says the same thing in different ways. So now we have a test. We know invertibility. And basically, what it says, I mean, what happens in the case of we have linearly dependent, we had many solutions. And if you have many solutions, you're mapping your vector into, something that like many things coming into the same place, similar to the x squared that we had. And then we couldn't figure out where it's coming from. So similar things would happen here. How do I prove this? Well, very easy, actually. The proof concept is the following. I need to prove that there isn't an A. There isn't. Well, how do I prove it? You also see that, by the way, in the discussion. So I'm just going to quickly just go over it. Okay. Assume, or homework, actually. Yeah, that's where we're going to see it. Assume linear dependence. So we're going to assume linear dependence, and we're going to assume invertibility. And then we're going to show that we get a contradiction. Okay. So I said, if it's invertible, if the columns are linearly dependent, it doesn't exist. Well, let's say it exists, and we'll get a contradiction, so it doesn't exist. Okay. Here's the idea. From linear independence, I know there is a vector alpha such that A times alpha equals 0. How do I know that? That's the definition of linear dependence. Okay, so it does exist. So A times alpha equals 0. There is one. And this alpha is not 0. Okay. Yeah, that's linear dependence. That's the definition. But now we're going to use the fact that A to the minus 1 exists, because we said it exists. So let's say it exists. So assume it's going to exist. And if it exists, then A to the minus 1 times A times alpha is also equal to A to the minus 1 times 0. Right? I just multiplied from the left side. But that says that identity, right? If this is the inverse, this is the identity times alpha equals 0. But wait a second, I said that alpha is not 0. Well, it has to be 0, so I get a contradiction. Therefore, a to the 1 minus 1 doesn't exist. K, Q, E, D. It's a really great station. All right. Now, in the last minute, I'm going to show you a trick. Okay, 1 minute, I'm going to show you a trick. If you have a 2x2 matrix, you don't have to do Gauss elimination. Okay, you don't have to do it. You have to do it once in order to prove this, but it's really easy to invert a 2x2 matrix. There's a trick. And the trick is the following. If you have A, B, C, D, you flip A and D, you switch between them. You're like, here, go here, and you go here. And then you negate these two. And then you divide by A times D minus B times C. Okay, this is the equation. You flip these two, you negate. And then you divide by A times D minus B times C. Okay, flip, negate, and then divide by the cross. A times D minus B times C. That's the equation. How do you get to it? You do Gauss elimination once, you get that equation, and now we can use it. All right, folks, we'll see you next week. Good luck on the quest. Watch leisurely the recorded lecture. You know, get a boba, you know, like your favorite, maybe a hot tea or cold tea or your favorite drink.
Water.
Water. Or light water or deuterium depleted water maybe, or deuterium enriched water. Maybe not so great. And just, you know, just watch the lecture and enjoy. All right? Ta-ta. Mwah, mwah, mwah. Bye, everybody.
Bye. See you in office hours.